Chapter 16, Segmentation. So far, we have putting the entire address space of each process in memory. With the base and bound registers, the OS can easily relocate the processor to different parts of the physical memory. However, you might have noticed something interesting about this address space of ours. There is a big chunk of free space right in the middle between the stack and the heap. As you can imagine from image 16.1, the overall space between the stack and heap is not being used by the process. It is still taking up the physical memory when it located the entire address space somewhere in physical memory. Thus, a simple approach of using the base and bound register pair to virtualize memory is wasteful. It also makes it quite hard to run a program when the entire address space doesn't fit into memory. Thus, base and bound is not as flexible as we would like, and thus, the crux: how to support a large address space. How do we support the large address space with potentially a lot of free space between the stack and the heap? Note that in our example, with the tiny pretend address spaces, the waste doesn't seem too bad. As I imagine, however, a 32-bit address space, 4 GB in size, the typical program will only use megabytes of memory, but still would demand that the entire address space be registered in memory. Section 16.1, Segmentation, Generalized Base and Bound. To solve this problem, an idea was born. It's called segmentation. It's quite an old idea, going at least as far back as the early 1960s. The idea is simple. Instead of having just one base and bound pair in our MMU, why not have the base and a bound pair per logical segment and over the address space? A segment is just a contiguous portion of an address space of a particular length, and in our canonical address space, we have three logically different segments: code, stack, and heap. When segmentation allows the OS to do is to place each one of those segments in different part of physical memory, and thus avoid filling the physical memory with unused virtual memory address space. Figure 16.1, an address space again. Let's look at the example. Assume we want to place the address space from figure 16.1 into physical memory with a base, bound, pair per segment. We can place each segment independently in physical memory. For example, see figure 16.2, page 171. There you see a 64 gigabytes physical memory with those three segments in it, and a 64 gigabytes reserved for the OS. In figure 16.2, place a segment in physical memory. As you can see in the diagram, only used memory is a located space in physical memory, thus large spaces with a large amount of unused address space, with sometimes the cold sparse address spaces can be accommodated. The hardware structure in our MMU required to support segmentation is just what you'd expect. In this case, a set of three base and bound register pairs. Figure 16.3 below shows the register values for the example above. Each bound register holds the size of the segment. Figure 16.3 segment register values. You can see from the figure that the code segment is placed in a physical address 32 kilobytes and has a size of 2 kilobytes, and the heap segment is placed in a 33 kilobytes and has a size of 3 kilobytes. The size segment here is exactly the same as the bound of register introduced previously. It tells the hardware exactly how many determined when a program has a legal access outside of those bounds. And then let's do an example of translation using the address space in the figure 16.1. Assume a reference made virtual address 100, which is the code segment. As you can see, visually in figure 16.1, page 170. When the reference take place, say an instruction fetch, the hardware will add the best value to the offset into the segment to 100 in this case to arrive at the desired physical address as 100 plus 32 kilobyte or 30,868. It will then check the address is within the bounds. 100 is less than 2 kilobytes. And then find that it is, and issue the reference to the physical memory address is the 32,868. So now let's look at the address in the heap. Virtual address is 44,200. Again, refer to the figure 16.1. If we just add the virtual address 4,200 to the base of the heap, 34 kilobytes, we get a physical address of 39,016, which is not the correct physical address. What we need to first do is extract the offset into the heap. That is, which bytes in this segment the address refers to, because the heap starts at a virtual address 4 kilobytes, 4,096. The offset of the 4,200 is actually 4,200 minus 4,096 or 104. When we take this offset 104 and add it to the base register physical address 34 kilo to get the result 34,920. What if we try to refer to an illegal address that is a virtual address of 7 kilobytes or greater, which is beyond the end of the heap? You can see imagine what will happen. The hardware will detect that the address is out of our bound, traps into the OS, likely leading to the termination of the offending the process. And now you know the origin of the famous term that all C programmers learn to read: the segmentation violation or segmentation fault. Section 16.2. Which segment are we referring to? The hardware uses the segment registers during the translation. How does it know the offset into segment and to segment of an address refers? One common approach is sometimes referred to an explicit approach to chop up the address space into segment based on the top few bits of the virtual address. This technique was used in the Vox VMS system. In our example above, we have 3 segments, thus we need 2 bits to accomplish our task. If we use the top of the bits, our 14-bit virtual address to select this segment, our virtual address looks like this: segment and offset. In our example, the top 2 bits of are 00. The hardware knows the virtual address is in the code segment. Thus, the uses code-based bound pair, the code base and bound pair to the relocate addresses the code correct physical location. If the top 2 bits are 01, the hardware knows the address in the heap and thus uses the heap base and bound. Let's take our example heap virtual address from the above 4,200 and translate it just to make sure this is clear. The virtual address 4,200 in binary form can be seen in here, the segment and offset. As you can see from the picture, the top 2 bits tell the hardware which segment are referring to. The bottom 12 bits are the offset into the segment 0000, 1001, 0110, 1000, or a hex 068 or 104 in decimal. that the hardware simply tasks the first 2 bits to determine which segment the register to use, and then takes in the next 12 bits as offset into the segment. By adding the base register to the offset, the hardware arrived at the physical address. Note that the offset erases the bound checks to. We can simply, the offset is less than the bound. If not, the address is illegal. Thus, if the base bounds were erased with 1 entry per segment 2, the hardware would be something like this to obtain the desired physical address. In our running example, we can fill in the values of the constants above. Specifically, seg mask would be set as set to 3000. Seg shift to the 12 and the offset mask 0xFFF. You may also have noticed that when we use the top 2 bits and we only have the 3 segment code heap stack and 1 segment for the address space goes unused. The fully utilized virtual address space and avoid unused segment to some systems put a code into the same segment as the heap and thus use only 1 bit to select which segment to use. Another issue with using the top so many bits to select a segment that limited the use virtual address space. Specifically, each segment is limited to maximum size, which our example is 4 kilobytes. Using the top 2 bits to choose call segment implies a 16 kilobyte address space gets chopped into 4 pieces, or 4 kilobytes in this example. If a running program wishes to grow a segment, set a heap and stack beyond the maximum, the program is out of the good. If there are some ways for hardware to determine which segment a particular address is in, and in simplicity approaches the hardware determine the segment by noticing the address was formed. If one example, the address was generated from program counter, that is, it was in section fetch, then the address within the code segment. If the address is based off the stack of the base pointer, it must be in the stack segment. Any other address must be in the heap. Section 16.3, what about the stack? Thus far, we've left out one important component of the space, the stack. The stack has been relocated to physical addresses to 28 kilobytes in the diagram above, but in one critical difference, it goes backward, that is, toward the lower addresses. In physical memory, it starts at 28 kilobytes and grows back to the 26 kilobytes, corresponding to the virtual address is 16 kilobytes to 14 kilobytes. Translation must proceed differently. The first thing, we need a little extra hardware support. Instead of just base and bound values, the hardware also needs to know which way the segment grows a bit. For example, a value set to 1 when the segment grows in the positive direction and 4 in negative direction. Our updated view of what hardware tracks is seen in figure 16.4. 16.4 segment registers with negative growth support. When themselves understanding the segment can grow in the negative direction, the hardware must now translate such virtual addresses slightly differently. Let's take an example. Stack virtual addresses and translate in order to understand the process. In this example, assume we wish to access the virtual address 15 kilobytes, which should map to the physical address 27 kilobytes. Our virtual address in binary form thus looks like this: 111100000000 hex 0x3c00. The hardware uses top 2 bits 11 to designate the segment, but then we are left with an offset of 3 kilobytes. To obtain the correct negative offset, we must subtract the maximum segment size from the 3 kilobytes. In this example, a segment can be 4 kilobytes, and thus the correct negative offset is 3 kilobytes minus 4 kilobytes, which equal to minus 1 kilobyte. We simply add a negative offset with minus 1 kilobyte to the base 28 kilobyte to arrive at the correct physical address, 27 kilobyte. The bounds of the check can be calculated by ensuring the absolute value of the negative offset is less than or equal to the segment current size, in this case 2 kilobytes. Section 16.4 Support for sharing. The support of the segmentation grew. The system designers soon realized that they could realize the new types of efficiency with a little more hardware support. Specifically, to save memory, sometimes it's useful to share certain memory segments between the address spaces. In particular, code sharing is common and still in use in systems today. To support sharing, we need a little extra support from the hardware in forms of protection bits. Basic support adds a few bits per segment, indicating whether or not a program can read or write a segment, or perhaps execute code that lies within the segment. By setting a code segment to read only the same code can be shared and across multiple processes without worrying of harming the isolation, while each process still thinks that it is accessing its own private memory. The OS is secretly sharing the memory, which can be modified by process. Thus, the illusion is preserved. An example of the address additional information tracked by the hardware and OS is shown in figure 16.5. As you can see, the code segment is set to read and execute, and thus the same physical segment in memory could be mapped into multiple virtual address spaces. Figure 16.5 segment register values with protection. With protection bits, the hardware algorithm described earlier would also have to change. In addition to the checking whether a virtual address is within the bounds, the hardware also has to check whether a particular access is permissible. If a user process tried to write to the read-only segment or execute from a non-executable segment, the hardware should raise an exception and let the OS deal with the offending process. Section 16.5 Fine-grained and coarse-grained segmentation. Most of our examples thus far have focused on systems with just a few segments, that is called stack here. We can think of this segmentation as a coarse grain, as it chops up the address space into relatively large, as coarse chunks. However, some early systems, for example Multics, were more flexible and allowed for address space to consist of a large number of smaller segments, referred to the fine-grained segmentation. Supporting many segments requires even further hardware support with segment tables of some kind of stored in memory. Such segment tables usually support the creation for a large number of segments and thus enable a system to use segments in more flexible ways than we have thus far discussed. For example, early machines like Broad the 5000 had support for 1000 segments and expected the compiler to chop code and data in separate segments, which OS hardware would that support to Arc68. The thinking at the time was that by having fine-grained segments, the OS could better learn about which segments are in use and which are not, and thus utilize the main memory more effectively. 16.6 OS support. You now should have a basic idea as to how segmentation works. Pieces of the address space are relocated into physical memory as the system runs, and thus a huge saving of the physical memory is achieved relative to our simpler approach with a single base bound pair for the entire address space. Specifically, All the unused space between the stack and the heap need not be allocated in physical memory, allowing us to fit more address spaces into physical memory and support a large and sparse virtual address space per process. However, segmentation raises a number of new issues for operating systems. The first time is an old one. What should the OS do on a context switch? You should have a good guess by now. The segmentation registers must be saved and restored. Clearly, each processor has its own virtual address space, and the OS must make sure to set up these registers correctly before letting the process run again. The second is OS interaction when a segment grows or perhaps shrink. For example, a program may call mem_alloc to allocate an object. In some cases, the existing heap will be able to service the request, and thus mem_alloc will find a free space for the object and return a pointer to its caller. In others, however, the heap segment itself may need to grow. In this case, the memory allocation library will perform a system call to grow the heap. For example, traditional Unix SBRK system call. The OS then usually provide more space, updating segmentation size register to new bigger size, informing the library of success. The library can allocate the space for new object and return successfully to the calling program. Do note that the OS could reject the request if no more physical memory is available, or if it decided that a calling process already has too much. The last, and perhaps most important issue in managing the free space in physical memory. When a new address space is created, the OS has to be able to find a space in physical memory for each segmentation. Previously, we assumed that each process space was same size, thus the physical memory could be thought of a bunch of slots when a process would fit in. Now we have the number of segments per process for each segment might be a different size. The general problem then arises that the physical memory quickly becomes full of the little holes of free space, making it difficult to allocate a new segment or to grow existing one. We call this problem standard fragmentation. See figure 16.6. In this example, the process comes along and wishes to allocate it to any kilobyte segment. In that example, there are 24 kilobytes free, but not in a contiguous segment, rather than 3 non-contiguous chunks. Thus, the OS cannot satisfy the 20 kilobyte request. Similar problems could occur when a request is grown a segment rise. If the next so many bytes of the physical space are available, the OS will have to reject the request even though there are free bytes available whereas in physical memory. Our solution to this problem would be a compact physical memory by rearranging the existing segment. For example, the OS could start whenever processes are running, copy their data to one contiguous region of memory, changing their segment register values to one contiguous region of memory, changing their segment register values to point to the new physical locations, and thus have a large free extent of memory with which to work. By doing so, the OS enables new allocation requests to succeed. However, compaction is expensive, as copying segment is memory intensive and generally use their amount of the process time. See figure 16.6 right for a diagram, compacted physical memory. Compaction also, ironically, makes the request to grow existing segment hard to serve, may thus cause further rearrangement to accommodate such requests. A simpler approach might instead to be use free list management algorithm that try to keep the large extent of memory available for allocation. There are literally hundreds of approaches that people have taken, including classic algorithm like best fit, which keeps a list of free spaces and return the one closest in size that satisfies the gyrus allocation to the requester, worse speed and faster speed, and more complex schemes like the Buddy algorithms. An excellent survey by Wilson et al. Is a good place to start if you wanted to learn more about such algorithms, or you can wait until we cover some of the basics in later chapter. Unfortunately, though, no matter how small the algorithm, external fragmentation will still exist. Thus, a good algorithm simply attempt to maximize. Section 16.7 Summary. Segmentation solves a number of problems and helps us to build a more effective virtualization of memory. Beyond just dynamic relocation, segmentation can better support sparse address spaces, and by avoiding the huge potential waste of memory between the logical segments of the address space. It is also faster, as doing algorithm segmentation requires easy and well suited to the hardware. The overhead of the translation are minimal. A fringy benefits arise to code sharing. If code is placed within separate segments such as could potentially be shared across multiple learning programs. However, as we learned, allocating the value of size segment in the memory leads to some problems that we'd like to overcome. The first, as discussed above, is external fragmentation. Because segments are very oversized, free memory gets chopped up into the outside faces, and thus satisfying the memory allocation request can be difficult. One can try to use the smart algorithms or periodic compact memory, but the problem is fundamentally and hard to avoid. The second, and perhaps more important problem is that the segmentation still is flexible enough to support our fully generalized and sparse address space. For example, if we have a large but a sparsely used heap or in one logical segment, the entire heap must still reside in memory in order to access it. In other words, in our model of how address space is being used does to exactly match how the underlying segmentation has been designed to support it. Segmentation does work very well. We thus find some new solutions, ready to find them. Reference and homeworks and questions.